Thank you very much, and thank you to the organizers for inviting me to this wonderful family reunion. Now, I would like to talk about Galois theory and valuation theory and model theory, but I would like to focus just on the field Q of rational numbers, just for simplicity. So, by way of introduction, I would like to present you three Galois conjectures. And when I talk about Galois theory here, what I mean is big Galois theory, where we not just look at finite Galois groups, but at absolute Galois groups, the kind of universal Galois group. So let me tell you what that is. If K is a field, then you can associate as an important invariant to it its absolute Galois group, which is just the Galois group of the separable closure of K over K. You can also think of it as being the inverse limit of the Galois groups of all finite Galois extensions L over K within a fixed algebraic closure. So it becomes naturally a profinite group this way, and this group is called the absolute Galois group. It's absolute in the sense that every Galois group occurring over the field is a quotient of it. Now, Galois theory plays a very important role in arithmetic. I mean, if you look into the in Andrew Wild's proof of Fermat's last theorem, it is a lot about Galois theory, and the Galois theory, the absolute Galois theory, absolute Galois group of Q knows almost everything about Q, and I will make that more precise in the course of the talk. So the first conjecture is the absolute Galois conjecture. So this is the absolute Galois conjecture. And this absolute Galois conjecture says the following. It says if K is any field, and if the absolute Galois group of K is isomorphic to the absolute Galois group of Q, then there is a Henselian valuation on K with residue field precisely Q and value group divisible. So then there exists a Henselian valuation V on K with value group, which I would like to denote by Vk divisible, and residue field, which I denote by Kv precisely Q. Now, the converse is, of course, also true just by general valuation theory. So this is an equivalence. And what makes one conjecture such things? Well, there are earlier results. So, for example, Neukirch has shown that if K is a number field, and then later Pop has generalized that to K being a finitely generated field, finitely generated over Q, and having the Galois group of Q, then the field actually equals Q. So within the class of number fields, due to Neukirch, and within the class of finitely generated fields due to Pop, the field Q is up to isomorphism determined by its absolute Galois group. So that tells you that the Galois group must know a lot about the field. And this absolute Galois conjecture, which I've put forward here, simply generalizes these things. So let me make an example here. So, or examples. One example is, of course, that k is equal to q, and then the Henselian valuation is just the trivial valuation. But you can also think of k being the Laurent series field with coefficients in Q, the field Q, and with exponents in the ordered abelian group of rationals. Or in fact, you can take any divisible, non-trivial divisible group in the place of it. That also satisfies that it has the absolute Galois group of Q, that is, again, easy, and it also satisfies the right-hand side, because the theoretic valuation here has, of course, divisible value group and residue field precisely Q. So, or another field which you may come up with is just if you take the union of the power series field in T to the 1 over n. This is, of course, elementarily equivalent by ex-quotient Yershov. So these are all natural examples where the right-hand side and the left-hand side of this conjecture are given. Now, I would like to present you a consequence of this conjecture, which tells you that if the conjecture is true, then the absolute Galois group really knows almost everything. And the consequence of the conjecture of the absolute Galois conjecture is, and this is again for k any field, that if the absolute Galois group of k is that of Q, and if the curve C has as many k rational points as it has q rational points, where C is a very simple curve. C is simply the elliptic curve given by the equation y squared equals x times x squared plus 1. Then k is equal to q. That means k is up to isomorphism determined by its absolute Galois group and by having on this curve only the rational point 0, 0, because that's what happens over Q, and if I ask that for k, then this simple property suffices to complement the knowledge about the absolute Galois group sufficiently well to determine Q up to isomorphism. Now, but this is only a consequence of a conjecture. So let me put a theorem here, and that is theorem 1, which is of a very different flavor, which says, again, k any field. So not just finitely generated, not number field, but any field. I say nothing about the characteristic, nothing. If gk is isomorphic to gq, and we have for all non-zero rational numbers that the curve CA, which I define in a second, has the same rational points over k as over q. And now what is CA? CA is just the curve given by the very similar equation, but a tiny bit more complicated. Y squared equals a times x squared minus 1 times x squared minus 4, for example. If that happens, so the field has the absolute Galois group of Q, and for this uniform family of genus 2 curves, it has the same rational points as over Q, then K is Q. And of course, all these arrows go back as well. Now, in particular, because this is a curve of genus greater 1, we know it always has only finitely many points. That means this property here can be expressed by, for each a single universal sentence. namely the universal sentence saying I, the curve CA, have no other zeros than blah, blah, blah.
At most 24 or something points.
Yeah, well, I just exclude the particular ones. And as a corollary to that, which of course uses Faltings, is that if the absolute Galois group is that of Q and K shares the universal theory, first order universal theory with Q, then K is equal to Q. And of course, the other way round as well. So this is another way of seeing it. The absolute Galois group and the universal theory characterize Q up to isomorphism. But as you see, I mean, we only use very little of the universal theory, only these very special sentences which come up here. Okay, we'll prove theorem 1 in the course of the lecture, but now I would like to introduce another version of this conjecture, a version which is more of a model theoretic type, and which is the following. So this is what I will call the elementary Galois conjecture. So the elementary Galois conjecture say? Well, it says something similar to the Galois conjecture, except that now we talk about elementary equivalence everywhere. So again, K is any field. And then the conjecture says that if the absolute Galois group of K is now not isomorphic to that of Q, but elementarily equivalent to that of Q. Now, of course, I should say in what language I'm talking here about. So talking about profinite groups in a first order fashion is not done by speaking about the group operation, because then you don't see the topology. So the way to do model theory for profinite groups is to talk about the inverse system of finite quotients of it. This is a multi-sorted language. For each size of a quotient, you have a special sort, and they are connected in natural ways. It's all well worked out by Jerlin, Fantendries, McIntyre, and Zoe Chatzidakis has done a lot of work on that as well. So it's well understood what it means for two profinite groups to be elementarily equivalent in that language, and that is what I mean here. Maybe the only important thing I should mention here is, because we only talk about certain finite quotients of the absolute Galois group, all this can be interpreted in the first order language of the field, because we are just talking about finite Galois groups or extensions of bounded degree. So it is all interpretable in the language of field. That's the important thing. And the conjecture says, very similar to the absolute Galois conjecture, that there exists a Henselian valuation V such that the residue field, I should start with the value group, such that the value group is divisible, and the residue field now not equal to Q, but elementarily equivalent to Q. That is the conjecture. And again, it goes easily the other way around. That is not difficult. So that means that if we have elementary equivalence of Galois groups, that gives us such an Henselian valuation where the residue field is elementarily equivalent to Q. And again, let me formulate a consequence of the elementary Galois conjecture, and that consequence is that if, and this is very much in the flavor of this corollary here, if the Galois group is elementarily equivalent to that of Q, and if the universal theory coincides, then K is elementarily equivalent to Q, and of course, it goes the other way around. So you can reformulate that by saying that the theory of Q, the first order theory of Q in the language of rings, is axiomatized by its Galois part, the first order theory of GQ, and as I was saying, this is really interpretable in the theory of Q, plus the universal theory of Q. That is a way of seeing this consequence of the elementary Galois conjecture. And what is nice about this is that we know the elementary theory of Q is undecidable. Whether or not the universal theory of Q is decidable or undecidable amounts to solving Hilbert's 10th problem over Q. Hilbert's 10th problem over Q, in logical term, asks whether the first order theory, the existential first order theory of Q is decidable. It's still wide open. So, because we know that Q is undecidable, either this guy or that guy must be undecidable. So either the high complexity, which makes Q undecidable, is already in here, or we have a negative solution to Hilbert's 10th problem, or both. But I think it's a nice application of this idea. Okay, now these conjectures, I mean, the absolute Galois conjecture has been around since the 90s, perhaps. This one is new, but it's a sort of natural extension. And I would like to motivate now how these conjectures came about in a geometric context. And this is talking about the third type of conjecture about the absolute Galois group of Q, which comes from Grothendiek and from his anabelian geometry. So that would be what is called the birational section conjecture, BSC. So birational section conjecture, which is due to Grothendiek in his program of anabelian geometry, and that says the following. That talks about curves over Q, so let C be a smooth projective curve over Q. Say with function field f. Then one has a canonical restriction map. And the restriction map goes from the absolute Galois group of F onto the absolute Galois group of Q, simply by taking automorphism of the algebraic closure of F over F and restrict it to the algebraic closure of Q. And the section conjecture says that every section S of this epimorphism, so then every section S of this restriction map comes from a rational point. From a Q rational point, say P in C of Q, which means that the image of the section lies inside a decomposition subgroup of GF with respect to P. So this dP is just a decomposition subgroup of the absolute Galois group of the function field with respect to the valuation induced on f by p. Now, what is this good for? This is good for, hopefully, having an effective way of finding rational points on Q, on curves over Q. So the hope is that this gives us an effective Faltings. Why is that? Well, because this is the crucial part of the conjecture, that every section comes from a rational point. But when one has that, one has more generally that there is a bijection between Q rational points on the curve and certain conjugacy classes of sections. And these conjugacy classes of sections are very well understood. They are parameterized by cohomology groups. So these are things one can lay one's hands on. There is a lot of computational machinery, and Grothendiek's hope was that to use this cohomological machinery if the sectional conjecture is true, in order to have a computational way of finding rational points on curves, which Faltings doesn't give. I mean, Faltings is, as it stands, ineffective, and this would be a great breakthrough if, in arithmetic geometry, if that was achieved. So that is the reason why people look at Galois theory in order to do arithmetic, because Galois theory is about groups, and there you have all the machinery of cohomology and what have you, which make things hopefully more effective. I will come to this issue of effectivity later on. Now, what kind of evidence do we have? Unfortunately, not too much yet. So, but there is some evidence there, and I will come to details in a second. What is so the best evidence so far is the birational section conjecture is true for I'm not very specific here, for some special curves. This was due to Jakob Stix in his Inventiones paper 2015. He gives families of curves where it's actually proved that every section comes from a rational point. These curves have genus 2 onwards. There was a preliminary result where he had examples where the birational section conjecture holds in a way trivially because there were no rational points and there were no sections. Which is something. I mean, it's a non-trivial result, but he has examples which actually do have points, rational points, and where all the sections come from these rational points. Now,
so like in genus 0 must be true.
Well, in genus 0, fine.
Yeah. I mean,
so, yeah.
There's also evidence. Is genus 0 trivial or not?
No, not at all. No.
Sorry,
no. Otherwise, we would be done, because you can always embed a genus 0 thing into any function field, and then no, it's not at all trivial. So even about over Q of t, no, it's really a very delicate issue. Theorem 2, I will indicate the proof of is the relation between those conjectures. It turns out that the elementary Galois conjecture is the strongest. That implies the absolute Galois conjecture, and that fairly easily implies the birational section conjecture. Essentially, the birational section conjecture is the absolute Galois conjecture in transcendence degree 1. That is more or less the case. But surprisingly, we have an equivalence here. So this shows that the old Grothendiek conjecture, in fact, is much more general. Okay, now, why do we believe some of these things? Well, of course, we believe them because they are true locally. So let me come to the local structure next. So, and the local picture fits very well. Now, so both the absolute Galois conjecture and the elementary Galois conjecture hold locally, which means they hold in R and in all QPs when you replace in the conjecture Q by these fields R and QP. Let me explain that. Now, first of all, we have that if K is any field, then you have that the absolute Galois group of K is elementarily equivalent to the absolute Galois group of the reals, which is just the group with two elements, if and only if it's isomorphic. And this is very simple because this is just a finitely generated group, and in fact it's just a finite group, and of course they are determined. Oh, thank you, yes. Of course we have no idea what GQ is. I mean, we have some conjectures, but we don't even know whether every finite quotient occurs. So even though we know very little about what GQ is, we can deduce from the structure of GQ almost all the arithmetic on Q, which is nice. Okay, so now this is obvious, and by Art and Schreier we know that this is the same as K being real closed, which of course by Tarski is the same as K being elementarily equivalent to the reals. And now comes the closest thing to the absolute Galois conjecture we can say, namely, this is equivalent, and this is perhaps a slightly strange formulation now, but you will see that it's true, that there exists a Henselian valuation V on K with value group divisible and residue field. Well, now at this point I cannot say equal to R because this will just not always happen, but a subfield of R. A subfield of R which is real closed. This is as much as we can say. So we can't expect it to be equal to R. And of course, you all know what this valuation is. This valuation has valuation ring just the convex hull of Q. So OV is just the convex hull of Q. I hardly need mention that in this audience. So that means the absolute Galois conjecture is as true as possible in this local sense. Let me go to the Padics. Let me see what happens when we replace GR by the absolute Galois group of QP here. Again, if they are elementarily equivalent, they are isomorphic because it's a finitely generated profinite group. And finitely generated profinite groups are up to isomorphism determined by their finite quotients. So that is why the elementary theory gives you already the isomorphism type. So that's easy. The next equivalence, that this means that K is p-adically closed, this is a theorem which started off with Neukirch and then was gradually generalized by Popp, and then finally I proved it in 1995 that the Padics, the elementary theory of the Padics, is encoded in its absolute Galois group. Efrat gave an independent proof for primes p greater than 2. So here, of course, we have to replace R by QP. This is then just ex-Kochen Hirscher in this case. Does everyone know what a p-adically closed field is? It's a field with a p-valuation. That is a valuation of mixed characteristic with residue field precisely Fp and value group a Z group, where the value of p is minimal positive. So that's the notion of p-adically closed. And then again, you have the same thing, that there is a Henselian valuation with divisible value group and residue field sitting inside QP and being p-adically closed. And again, we can explicitly give that valuation. Here, the valuation ring is if Vp is your p-adic valuation on the field, is just Vp adjoined 1 over p. So maybe I should make examples here. So, of course, if K is itself QP, this is an example. But another example would be that K is only the algebraic part of QP, so which is just QP intersect with Q bar. Or another example is the Laurent series field over QP with coefficients, say, in the divisible group Q. These are all examples of p-adically closed fields, and they all satisfy this absolute Galois conjecture over QP. So you see, locally, these conjectures are fine. So what we have to try and do now is bring from local down to global, to the global fields. Let me try and explain a bit of that in the next paragraph. So this is from local to global. And for that, I would first like to talk about what we know for sure, that the absolute Galois group of K, being that of Q, tells us about K. So let's have a proposition here. So again, K any field. And now assume that the absolute Galois group of K is isomorphic to that of Q. Then we have a couple of properties. The first one is, and that is straightforward, that the characteristic of the field is 0. There are many ways of seeing this. One is, of course, that the absolute Galois group of Q contains involutions, hence real closures, and hence, of course, it must be of characteristic 0. But now we are given this abstract isomorphism, and this abstract isomorphism is very hard to connect to the fields itself. And luckily, it turns out that however our abstract isomorphism is given, the natural homomorphism from the absolute Galois group of K onto that of Q is, in this case, itself an isomorphism. So, and the restriction map from, I mean, this of course tells you that Q is a subfield of K, which tells you that there's a natural restriction map from the absolute Galois group of K to that of Q, and that then happens to be an isomorphism. This is a non-trivial result one can prove. Now, the second thing, using the local picture here, we obtain that for every prime p, there must be a p-adic valuation and a unique p-adic valuation on K. So for every prime P, there is a unique p-adic valuation, say Vp, on K, and of course there is a unique ordering. There is a unique ordering. And I'll indicate the proof in a second, but that follows more or less straightforward from the local theory. But let me just list a few more properties here. Now we have this family of p-adic valuations and orderings, and it turns out that the field K obeys almost all theories of algebraic number theory with respect to these things. So K satisfies, let me be vague, most of algebraic number theory with respect to these Vp and the ordering. So let me just give a few examples. We have that every finite extension ramifies at only finitely many points. So every finite L over K ramifies only at finitely many P. We have the Chebotarev density theorem. We have the Hasse-Minkowski local global principle for quadratic forms. We have the Kronecker-Weber theorem that the maximal abelian extension is obtained by adjoining roots of unity. We have quadratic reciprocity law. All these things.
Do you have a ring of integers?
Sorry?
Do you have a ring of integers inside K?
You do have a ring of integers, namely the intersection of all the p-adic rings. But in general, we don't know whether that is bigger than Z. I'm sorry to tell you. Yes. It may well be, and of course in the conjectured case it is much bigger, and we know precisely what it should be in the conjectured case, but in general we have no answer to that question, I'm afraid. So, but still it tells you that the Galois theory knows a lot. That means all those things from algebraic number theory are in fact Galois theoretic properties, as it turns out. So this brings us already in the direction of the absolute Galois conjecture. But now let me give you a brief proof of theorems 1 and 2. So proof of theorem 1, so we assume that the absolute Galois group of K is that of Q, and then we have all these facts here, and so assume GK is isomorphic to GQ, but K is different from Q. So pick an element X in K which is outside Q, and then we know by the first property that the restriction map is in fact an isomorphism. We know that in particular the square classes map bijectively onto each other. That means we know that there must be an element, a non-zero element A in Q such that A times x squared minus 1 times x squared minus 4. I mean, this is just a certain element, non-zero element from K, and then because the squares are represented by elements from downstairs, we know that this must be, for some A, this must be a square in K. And hence, we have, say, this is y squared, and hence we have that the point xy belongs to the curve CA, the k-rational points of the curve CA, but clearly not because it's transcendental. I mean, this is easy to see that this is transcendental, but not CA of Q, which violates our assumption. So that shows how Q is uniquely determined by its absolute Galois group, and these few sentences about this uniform family of genus 2 curves indexed by A.
I don't understand why you needed that particular curve.
I don't. This is.
Why is it complicated? Why not just?
Well, I could say let f be any irreducible polynomial of degree greater than 4, and y squared equals f of x. Oh, there's nothing special about that. No, I've just taken something you can.
What the degree 4? You needed something.
You want genus greater 1.
Okay, well, that's the only thing.
That's the only thing. That's the only thing. I just want genus greater 1. Yeah, yeah. Okay. Let me go to theorem 2. So this proves theorem 1. Now, as for theorem 2, well, the first thing, why does the elementary Galois conjecture imply, so the absolute Galois conjecture? Well, that is because assume we are in the situation of the absolute Galois conjecture having a field whose Galois group is isomorphic to that of Q, then of course it's also elementarily equivalent. Then by the elementary conjecture, there's a Henselian valuation with residue field elementarily equivalent to Q. But then there is no field other than Q which is elementarily equivalent to Q and has isomorphic absolute Galois group. Why? If it did, then the restriction map would be an isomorphism. But if you have a non-standard rational field, so a non-standard extension of Q, then you always have new primes around, and they give rise to new square classes, and this cannot be. So it's very simple. So that is really straightforward, just using that non-trivial fact that if you have an isomorphism at all, then the restriction map is an isomorphism. Which comes, by the way, from, well, I should say something to the proof of proposition as well, but let me just finish the proof of theorem 2, and then I'll get back to that. Now, here, as I was saying, the arrow from left to right is obvious because the birational section conjecture is essentially the absolute Galois conjecture in the special case of transcendence degree 1. But why does transcendence degree 1 suffice for the general thing? So why does the birational section conjecture imply the absolute Galois conjecture? That is because if you have now an arbitrary GK, which is isomorphic to GQ, and suppose K is different from Q to make it interesting, and then we look at intermediate fields, so for all fields L which sit between Q and K, such that the transcendence degree of L over Q is 1, and L is relatively algebraically closed in K. So L is L tilde intersect K. Then you get that the restriction map from GK to GL to GQ, you know the compositum is an isomorphism, and then all of these in between must be isomorphisms. And so now, because this is transcendence degree 1, we assume the absolute Galois conjecture for that. That means on L, we have such a Henselian valuation. But that implies that, in particular, that implies that for all primes P, say, and Q, we have that the Padic valuation coarsened by adjoining 1 over P. That's the one I was introducing up here. So let me just call that one O VP tilde, this rank 1 coarsening of the Padic valuation. That has then a non-trivial maximal ideal. And this is the same as the maximal ideal of the corresponding Q-adic rank 1 coarsening. This is on L. But then the same thing holds on K, and then this VP tilde for any of these primes, but now on K, does the job. So once you have this proposition, it's not so difficult to deduce that, in fact, it suffices to do the transcendence degree 1 step. Now let me very briefly indicate the proof of the proposition.
So the equality of the ideals comes from 2.
No. On L, we know there is a Henselian valuation with residue field Q. This must be the VP tilde here. And it's the same for all P. And that is something I can write down. And that simple observation, that it's the same for all P, that goes from arbitrary K down to, from transcendence degree 1 to arbitrary ones. And that is how it works. A very brief indication of why the proposition comes out as nicely as it does. I don't say proof of proposition, but just a picture of what's happening. What is happening is that the absolute, if you have an isomorphism from GK to GQ, this is your isomorphism, then you may want to consider the subgroup of GQ, which is GQP of the algebraic part of the Henselization of Q with respect to Q. This is a subgroup, and I can lift that over to here. So let KP be the fixed field of phi to the minus 1 of GQP algebraic. Then the picture is the following. Then we have, here's the isomorphism from GK to GQ. In here is sitting GQP algebraic. That's sitting in here. The isomorphism, I've taken it back to give me the GKP, which is sitting in here. And now you use the fact that the absolute Galois group is generated as a profinite group by the GQP algebraic, where P runs through all primes. Well, in fact, it suffices a density 1 subset of primes for that, but anyway, we have it all. So we must get the same picture over here, that the absolute Galois group of K is generated by the absolute Galois group of these Kp's, where P runs through all the primes. And this gives you the recipe for proving this, where it is important to note that for this isomorphism here, that if GK is GQP, that this isomorphism, I should do that in green, this isomorphism respects inertia subgroups and ramification subgroups. So we know that K is p-adically closed again, so it has, the absolute Galois group of it has an inertia subgroup, a ramification subgroup. Any isomorphism respects those because they are characteristic subgroups, easily described. So that is why all the ramification data is carried over from Q to K, and that is why this proposition works here. Now, let me just make a final remark on effectiveness. So I said that there is a hope of getting an effective Faltings. And of course, we are still far from that, but there are a few places where our procedures, even though they look very abstract, can be made effective. And that is in particular when we try and prove the elementary Galois conjecture over there. Because what we are talking about there is not about absolute Galois groups, but about finite quotients of them. And for example, in order to detect in a Galois group GK, which is elementarily equivalent to GQ, in order to detect in there periodic valuations, you need bounds on your degrees, how far you have to go in your quotients in order to find that. So that is why this is a stronger thing, the elementary Galois conjecture, and if it's true and will be proven, it leads to a much more effective version of the proposition over here. So EGC gives more effective results and is therefore more in the direction hoped for by Grothendiek in correcting Faltings' proof. And we could actually prove a few things in this direction. For example, you have that if GK is elementarily equivalent to GQ, then again, there is a unique p-adic valuation, and there is a unique ordering on K, and this could only be obtained by obtaining finite bounds. For example, if GK is elementarily equivalent to GQ, how do you detect that the Galois group contains involutions? Yeah. That is not easy. You have to say for each Galois extension of degree n, if there is an element of order 2, that you have a certain Galois extension of a higher degree, of course, where that remains an element of order 2. And this is, if this was n, the bound we have is something like 2 to the 2 to the n. I mean, it goes very high up, and is, of course, in that sense, not awfully effective, but it can be pinned down in principle, and the same for the p-adics. And there have been, I mean, also in this result about the Galois group of QP, we take the full, which is an infinite profinite group in order to characterize it. However, there has been very recent progress by Florian Popp and Jakob Stix. They come up with just a finite amount of information. We only need a certain finite quotient of the Galois group of QP in order to detect the p-adic valuation, and there's a lot of work in progress in this direction. So there are several ways of making this general picture more effective, and then hopefully in the end arrive at something like an effective faultings, and this way have valuation theory help along with arithmetic geometry. Maybe I'll stop here.
Questions, comments? Sorry.
Oh, okay. So just maybe a naive question. Are there analogs of this conjecture if you replace Q by a function field?
In positive characteristic? Yeah? Global function field?
Yeah.
Everything is false.
Everything is false.
Roughly speaking. No, of course, there are results in this direction. If a field has the absolute Galois group of a function field in positive characteristics, you can say something, but so much less. Because, first of all, you can go to the perfect hull, and this is not seen by Galois. And then, with wild ramification, a lot of terrible things happen, so much less is known. However, what I should say is that all of these conjectures were, of course, not just made for Q, but at least for number fields. So everything on the board, conjectured on the board, is also being conjectured for number fields. And in fact, the absolute Galois conjecture should also be conjectured for finitely generated fields. Not the birational section conjecture, that's false. But the absolute Galois conjecture and the elementary Galois conjecture, they should go through for finitely generated fields over Q. But this is far away.
I didn't get, how do you get the valuation actually from the group structure? That is really a valuation. So you have an inertial group and all these decomposition groups. And
here,
yeah.
Well, this is a big machinery, and it's a much more general machinery. You get it via rigid elements.
I remember a talk of yours many years ago. Yeah.
That's the key word. Now, the point is, you have to look. If you have as absolute Galois group, something like this, which is, for example, maybe I should change that to Q, which is another prime, which is, for Q, different from P, the Silo Q subgroup of the absolute Galois group of Q. Mm. That is the key object from which you should read off a valuation. And how do you do that? This condition tells you something about the images of norms being very small, and then you work explicitly with these norms, and they tell you that there are lots of rigid elements around, and they give rise to valuations. So there is a very general recipe for detecting valuations in absolute Galois groups. Namely, there is a bijection between tamely branching valuations on a field K and certain subgroups of the absolute Galois group, and tamely branching simply means that the valuation is has a value group which is not P divisible for a prime P which is away from the residual characteristic. And then there's a few exceptional cases. But that's a very general picture. All these valuations are encoded in the absolute Galois group. And that is what is behind that. But this is the crucial example you have to work. This is
some other question?
No. Is there a special thing about P or Q equals 2? Yeah. There was this rigid theory before in quadratic forms.
That's right. Yeah. The rigid stuff started off with quadratic forms, where it is as complicated as it can get. Mm-hmm. Life is easier for P greater than 2, but one didn't have the machinery at that time. So one had to invent a completely new machinery in order to work with these rigid elements for P greater than 2. And that happened in the 90s. And so, yes, it's a completely new machinery had to be invented, but then it works very much along the same line as the quadratic situation. Yes, and of course it was kicked off by the quadratic picture.
Some other questions?
So in a section conjecture, if you have this S, is it then automatic that the image avoids the ramification group so that the intersection is 0?
Yeah, yeah, that just so happens. Yeah, very good.
So long?
Is there a formal implication known that, for example, BSC implies effective faultings, or is that just still a hope?
That is a hope which has been worked out by Min Young Kim in a very famous Involutions paper, I think in 2005. I'm afraid very few people understand this. And he's my neighbor in Oxford, and I talk to him a lot, and we get on very well.
Oh, okay.
But I don't understand too much of it. But there is stuff around there, very deep homological, non-abelian cohomology stuff, which sort of supports this.
Are there some other question or some comment? So, nobody? So, let's thank the speaker again for this wonderful talk.
Thank you. Thank you very much.